First of all, I would like to thank the organizing to allow me to speak today. I'm from the work of from the group of Chiara Saffirio in the University of Basel, and today I will talk about the dynamic of BEC in a Thomas-Fermi regime. Maybe I will also give you the meaning of BEC later on. And this is based on an ongoing project with Emanuela Giacomelli, Michele Correggi, and Peter Pickel. Also, those slides, you can find them on my webpage right now, and the webpage is daniele.dimonte.it. So I think I can start, and I will first give you a little bit of an introduction and the reason why we studied this problem. Then I will go more into the details of the dynamical problem that I want to describe to you, and then I will finish with a little bit of conclusions on this topic and maybe some perspectives. And I begin with the introduction, and first, the generic goal, so in the study of many-body quantum mechanics in a system of bosons, usually one can deal with the study of the dynamic or the ground state problem of n-identical bosons in a box, and usually with maybe with some boundary condition, when periodic boundary condition, for example, and usually one deals with the study of a thermodynamical limit of a system, which is a limit in which we send the size of the box to infinity, keeping the density constant. And in this case, one quantity that is usually looked at is the energy per particle, just the fraction of energy over the total number of particles. And this turns out to be a right quantity to look at, for example, and in a seminal work by Li Wang and Yang, it was proven that turns out that the approximation of this energy per particle can be expressed only in terms of what is the scattering length of the potential, so some effective quantity related to the per potential of the system, and the density of our gas, in a sense. And so this is what is called usually the dilute limit, meaning that we keep this rho a cube quantity really small, a indicating the effective length of the interaction, and rho the density. So this is more or less the density of the gas in the total volume when we send the box to infinity. And this formula was actually proven only recently in 2019, the lower bound part at least, by Fournet and Solovey. So this is a little bit of the reason why one could be interested in the dilute limit of a gas. And in general, for this dilute limit, at least at zero temperature, one can expect that the ground state, for example, of the many-body system is well approximated by a state which is just the product, at least in first approximation, of an identical state in every particle. So we're thinking about the system in which all the particles sits in the same state, and this gives us the possibility to approximate the many-body potential with an effective potential, which will be an average over all the other identical particles on a single particle. So what turns out to be the case is that maybe studying the ground state of the system and studying the ground state of an effective one-particle system can be related in some sense. And the energy that one can study for the single particle system can be just obtained by the single particle of the Hamiltonian and an effective interaction coming exactly from some sort of interpolation of the other particles. So how does one describe this from a mathematical point of view? Usually is encoded in the interaction that one puts into. So one simple interaction is the so-called Hartree interaction, which is just a mean field interaction. And the effective interaction that we turned out to see is sort of a convolution with the density of a single particle. And what we're looking at the right side is just the energy term. Of course, if one consider the dynamics, we'll have a corresponding nonlinear term. And so for the mean field, what we see is a sort of a convolution term, which is encoded in what is called the Hartree energy. More commonly, or more interestingly in a sense, is the Gross-Pitayevsky interaction, which is given as in this n square Vn x. And this is also obtained by some rescaling of the box. And the effective energy term that we obtain is a quartic term in the state. And then one can consider some intermediate regimes, and I call them intermediate because it turns out that the same two cases of the mean field and the Gross-Pitayevsky are just extremal case of this intermediate regime, and this was deeply used to prove some results for the ground state energy, at least for the Gross-Pitayevsky interaction. And the effective interaction, the effective term that we see in the energy is still a quartic term, but instead of having some quantity g, which is related to the grounds, to the scattering length of the potential, we find just the integral of V. In all of these cases, what is interesting is that the scattering length goes to a constant, and if the scattering length goes to the rescaled scattering length, we multiply the scattering length by n, and this goes to a constant, and if that is the case, one can easily see that this is indeed a dilute limit. And so this is a good model to approximate then the energy per particle in the thermodynamical limit. But turns out that in more experimental settings, what we can observe is that the scattering length times the number of particles is not close to a constant, but it is actually a big quantity. So an interesting regime that one might be interested in is the so-called Thomas-Fermi regime, in which the scattering length times the number of particles just goes to infinity instead of going to a constant. And so what we will do in the rest of the presentation is consider some sort of a Thomas-Fermi limit in which we will need to still implement the condition that is a dilute limit. But if we are able to do this, this is a good guess for a Thomas-Fermi limit, really. And again, this is an interesting setting when considering, for example, rotating Bose gases and stuff like this. So the candidate for the Hamiltonian that I want to discuss with you today is a sort of a many-body Hamiltonian, which in a trap box now, in which the size of the box is fixed, so we don't send the box to infinity, but in a sense there is a rescaling going on. And I will talk about the box, but of course, similar results can be proven also in a three-dimensional setting with a trapping. It's just a matter of rescaling some dimensions there. And the Hamiltonian that I consider is just a kinetic term implemented by the Laplacian, and then an interaction encoded by pair interactions with the scaling, which is now similar to the one that we saw before, for example, for the mean field regime, but we put also this constant g of n in front of it. And so when we do, so of course the many-body Hilbert space is just a space of a symmetric wave function on n particles, and without loss of generality, of course, we can assume the integral of the potential to be constant and to be equal to 1, because any constant we can just move it to this constant Gn. And if we consider a potential of this form with beta in between 0 and 1 strictly less than 1, the scattering length of this potential times the number of particles goes as this constant G of n that I put in front of the potential. And so if we want to implement the Thomas-Fermi regime, a good question that we could ask, or a good condition that we could impose, is that this constant G of n goes to infinity as the number of particles goes to infinity. And we still have some room, in a sense, to implement the dilute limit, just asking that this goes to infinity, but not so fast, just as a power of n. And then one can easily see that this is still a dilute limit. So, in particular, in discussing the concept of Bose-Einstein condensate and condensation, it is useful to remind you of the definition of what is a one-particle reduced density matrix. One particle reduced density matrix associated to a state is just the operator that is associated to a projector along a state psi, which is helpful to consider one particle observable of the system. I think this is probably familiar to most of you, but anyway, if we consider a one particle observable on a state, we can encode this just in the trace of the operator itself with the effective operator that we call the one particle reduced density matrix, which is just the trace, we trace away the additional degrees of freedom of our projector to just consider one particle operator. And condensation in this framework will be encoded in the fact that this reduced density matrix is now converging to a projector along a single state phi. And if you think about it a little, this will tell you basically that when you want to consider the expectation of a one particle observable, in the limit is enough to consider the expectation on this effective state phi, for example. So we say that we have Bose-Einstein condensation in a state phi for the state psi if the one particle reduced density matrix converges to a projector along phi. And I put here in sigma 1h, meaning in trace class, but it turns out that given that the projector on phi is a rank 1 projector, this convergence can actually be expressed also as Hilbert-Schmidt convergence, norm convergence, or in different ways. And all these convergences are equivalent in the case of a rank 1 projector. And so we say trace norm, but you could choose your favorite topology, and this will still be true. Okay, and so, yeah, so this is the concept of Bose-Einstein condensation. Our particles are mostly sitting in the same state, and this is what I wrote in the previous slide as an approximation of the psi. So now let's get to the dynamical problem, and the dynamical problem is again the same Hamiltonian. We consider the same Hamiltonian. Now the box is more explicit here. And we consider the solution of the Schrödinger equation, just the many-body Schrödinger equation with a sort of initial datum. And the question that we ask ourselves is, if I assume to have Bose-Einstein condensation at the initial datum on an initial datum phi 0, can I find, first of all, can I prove that there is Bose-Einstein condensation also at later times? And second of all, can I find a time evolution for the state on which I have condensation? On this same note, let me just say that we are working also on proving that there is condensation in the ground state for an energy of this kind. And so this is a question that, in a sense, makes sense. So a little bit of a spoiler is that there is, we believe that there is a description for this state, and the description of this state is encoded in a time-dependent Gross-Pitayevsky equation. It's really similar to the Gross-Pitayevsky that we know and love. So this is a nonlinear cubic Schrödinger equation, but as you see, there is still a parameter g of n in front of the nonlinearity, which makes it a little bit interesting because we are not expecting at this level that the effective dynamic is completely n independent. So we expect this not to be a full limit n going to infinity, but sort of an approximation for the number of particles being really large. If this is a little bit striking for you, well, this is actually a well-studied model when minimizing sort of a Thomas-Fermi limit for the Gross-Pitayevsky energy, where this g of n is usually encoded in a small or large parameter, depending on where you put it. But so we really need to think of it not as a full limit, but more like an approximation for a large number of particles. When considering this kind of equation, even if it is a nonlinear equation, we still have a conserved energy. This, of course, conserves the L2 norm, and in particular conserves also the what I call the Gross-Pitayevsky energy that you see written here, and we see the quartic term that we saw before also when describing the energies. And one crucial idea when consider this kind of energy is that when this parameter g of n now is really large, we can expect the kinetic term to be subleading with respect to the other terms. Now, if you know a little bit about this problem, this is a sort of a trivial statement in this case, because in the ground state, the state is just a constant. So in the constant state, the kinetic energy is not there. But this is a more generic property, and if we consider a trap system in 3 dimensions, this is still true that the kinetic energy is subleading with respect to the rest. And in particular, in this case, it's useful to consider what is called the Thomas-Fermi energy functional, which similarly to the theory for large atoms, is a theory for the densities in which we threw away the kinetic term. And again, in this particular case, the Gross-Pitayevsky energy, so the ground state of the Gross-Pitayevsky energy, is identical to the ground state of this Thomas-Fermi energy and explicit, but in different cases, this is still true. And so it's just remarkable to notice. But it encoded some properties that we want to exploit for our result. And so what I wanted to say is also that, in particular, when I discussed before about the mean field and the Hartree limit, you notice that the mean field was giving me a convolution, while as long as I have a beta different from 0, I get the quartic nonlinearity. And what it turns out to be the case is that it is useful to consider an intermediate regime in this case, which is a sort of, again, a convolution term with a potential V of n. And this is called the time-dependent Hartree equation. And to consider then the limit Hartree to Gross-Pitayevsky in a separate way. And to do so, one exploits the fact that the Vn goes to a delta, so the convolution with the Vn goes just to the state itself. But in order to do this further approximation, one needs to use the fact that one has some control on the L infinity norm of the solution. Unfortunately, this posed a really hard question to us, and in the end we were forced to put it as an additional conjecture to prove our result. And the conjecture is that if you consider an initial datum which has L infinity norm bounded, and let's say independently of n, which is a condition that we need to implement if we're considering just approximation and not full limits, then the supremum for any time should be bounded. And this can be expected in some sense. So we expect this conjecture to be true. And if we assume this conjecture, we were able to prove that under suitable condition on the potential and suitable condition on which I will discuss a little bit in the next slide, one is able to prove that, at least in Train's norm approximation, the reduced density matrix of the projector on the state psi and t solution of the Schrödinger equation is close to the projector on the solution of the Gross-Pitayevsky equation. So, yes, so this is exactly what I was telling you before. One is not able to prove a full limit at this level, but is able to prove that the difference in norm is small when n goes to infinity. And so a little bit of comments on this condition here that we see on the slide. And first of all, we are able to achieve similar results in actually different dimensions, in particular in dimension d equal 2, which is specifically important when one is interested in rotating condensates. If one wants to just study the two-dimensional problem, we are still able to achieve something there. But it's still an open problem in our in this problem for us to go beyond the critical value beta equal 1/6. And this is related in a sense also to some problem for the ground state problem. Indeed, as I told you before, we are also working on the ground state problem, but for the ground state problem right now, we're able to achieve only results for even smaller quantities, even smaller amounts of beta, and so one really needs to wonder if it's possible to go beyond this threshold. And then I showed you before that there are these three hypotheses in a sense, and these three hypotheses encodes different conditions. And the first one is the condition that I have condensation in the initial datum. I of course expect to have condensation in initial datum if I want to observe this condensation to be present also at later times. The second condition is an energy condition, and is asking me that the Gross-Pitayevsky energy of the initial datum is close to the ground state of the Gross-Pitayevsky energy in general. And this is helpful in particular to approximate the Hartree to Gross-Pitayevsky. So in a sense, one could achieve a better approximation with the Hartree equation, but then it's a little bit more involved with the parameter. So it's better to get to the Gross-Pitayevsky, but in order to do so, we needed to assume that the energy of the initial datum is low enough. And then there is a third condition, which is a condition that we need to prove condensation, meaning that this constant g of n that we assume to go to infinity goes to infinity, but not as strong. So as I told you already, we have already a condition on the growth of this constant g of n due to the dilute condition, and there's an additional condition required to prove condensation on a general level. And so these are sort of three crucial hypotheses that we need to. And then, of course, some hypotheses on the potential, but yeah, this is expected in this framework. So I will give you just a quick sketch of the proof, and the proof is done in two steps, mainly. One first approximate, as I was telling you, the one particle reduced density matrix with a projector on the Hartree solution, and then approximate the Hartree solution with the Gross-Pitayevsky solution, exploiting the fact that the potential is going to a delta. So to do the first step, we use some tools developed in a previous work by Peter Pickel. And then for the second part, we really use just energy estimates and the idea as before. And so for the work of Pickel, it's a little bit more convoluted than this, but the idea in general is just the fact that if we consider this quantity alpha of t, as you can see, is just how much of my state is in the one particle state phi t, because given the symmetry of the state, this is a quantity that, so first of all, this is a projector, so this is a positive quantity, and given the symmetry of the state, if my state is really close to a factorized state, the right quantity is really close to 1. So at the initial time, this quantity is more or less 0, and if time increases, we expect this quantity to be small as well. And so what one does is to study a Grunwald type estimate for this quantity, and after we have some growth for the alpha of t, is enough to prove that this is equivalent to the trace norm convergence, but it's also easy to prove, and it was done in several papers that these are equivalent conditions. One crucial point at this level is that one needs to estimate terms of the form L infinity of the convolution of the potential with the solution, and given that the solution goes to a delta, one can expect that this quantity is related to the L infinity norm of the solution. We all know Young inequality, so actually one could try to put different norms on the potential and the Hartree solution, but what turns out to be the case is that different condition will give me a growth in n of this quantity here, which plays a really bad role in the condensation, and so as long as you don't take the L1 norm of the potential and the L infinity norm of the solution, we were not able to prove condensation anymore. And so this is another point in which the L infinity norm of the solution plays a crucial role, and the conjecture as well. But using the conjecture, we are able to control this term, and we're able to conclude. Yeah, a comment that I wanted to make also related to this is that, as I was telling you, we're not able to prove condensation unless we require that the times are just living on the now time scale depending on n. And one could do that, it's a little bit artificial in a sense, and compare with the results of rotating condensates. Turns out that the time that one can observe, even if n-dependent, are not enough to capture some physical properties like motion of vortices in rotating condensates, or even like fluid, superfluids in general. And so this was not enough for us to achieve the result that we wanted. And so we had to assume the condition also in this case. Then the next step, as I was telling you, is the approximation Hartree to Gross-Pitayevsky. And to do so, we just study the L2 norm of the difference, and we try to achieve some bound for this quantity. And we clearly have that this derivative is bounded by just the difference of the nonlinearities. And the difference of the nonlinearities have one term that encoded the convergence to a delta, and one term which is just the difference of the quartic terms. And so one bounds this using the fact that the energies are close to the ground state energies, and then bounds this by the fact that the Vn goes to a delta, and is able to conclude using also the conjecture, and that's it. This is basically the idea. So I will just move now to the conclusions. I don't know how fast I was. I hope not too much. And so some conclusions on this matter are that first of all, we proved that condensation is preserved under suitable condition. And now the two main questions are, of course, how can we prove the conjecture? And this is a deep analysis question. We were not able to find explicit bounds on the cubic nonlinearity that would allow us to control the L infinity norm in terms of this Gn constant. And this is a crucial point to achieve any result in this setting. And then, of course, we wonder whether we can extend these results for larger values of beta. And this, again, as I told you before, related to the ground state problem too. And another related question is also that, as I told you before, these are interesting questions for rotating Bose-Einstein condensates. And in rotating Bose-Einstein condensates, we have also vortices usually, or like excitation of the energy are expressed through presence on vortices usually. And one can observe motion of vortices and stuff like that. And in general, studies of vortices in this framework is related to the study of what is called the measure of vorticity, for example. But the measure of vorticity on the state is encoded in some quantity with the gradient of the state. And any results that I showed you today is related only on the convergence of the one particle reduced density matrix. So we're not able to catch any property of the gradient or any property of the solution despite the one particle reduced density matrix. And this means that, for example, to observe vortices at the many-body level using the theory for the effecting theory for the single particle, one will need some stronger kind of convergence. And so this is another direction in which we would like to move forward in the future. So I think this is more or less all I wanted to say. So thank you for the attention. And yeah, I'm open for questions if you want.
Oh, thank you. Any questions or comments?
You have an assumption on the energy, on the Gross-Pitayevsky energy of the initial state, but none on the quantum mechanical energy of the initial state, despite the dynamics being the quantum mechanical one. Isn't that sort of surprising? I mean, you can have a state which is close to the condensate in norm as much as you like, but in energy is still very different. It's not an issue.
Well, I would argue that probably this would be encoded in the effective, of the energy of the effective state, right? I mean, if I have a state that has a condensate on a single particle state, which energy is close to the ground state, one could argue that this implies that the energy of the many-body state is close to the ground state energy. But this is not part of the condition. So we were able to achieve the result with only a condition on the effective state in a sense. But your question is, of course, saying that I could argue that this is a question on the initial datum. But keep in mind that probably if we want to achieve convergence to the Hartree solution, the energy condition is not necessary. And so we could expect that if I have condensation at initial datum, I have condensation at a later time independently from the energy. Of course, condensation in something that is a solution of a deeply independent problem. So that's a little bit the question. But in a sense, the energy condition at the initial datum for the many-body problem is really encoded in the energy condition for the effective solution, in a sense. I hope this answered the question.
Well, there are no more questions. Thanks again.